Okay, so it appears to be 4:25 on Thursday afternoon, 10:65 here. So let's go ahead and get started. Sorry, I actually muted myself there. Um, Welcome to this week of ETECH 899. We'll continue on this week with our discussion of optimization. And this is kind of the last really part of this continuing thought of mathematical optimization, kind of the way we have been thinking about it. We started off the very first of the semester talking about linear programming, how to form linear models. We've gone through that quite a bit. We recently talked about integer linear models, right, from last week. So hopefully you guys looked at that and said, okay, wow, there's a whole another realm of problems I can now solve, especially when we talk about MIP problem, mixed integer programming problems, where you've got these decision variables that are binary in nature, that can do these if-then type of logic that's built into the models themselves there. And so up to this point in the semester, everything has been linear based. That's been a key trend, right, throughout every model you've written so far, is the fact that everything in the objective function, everything in the constraints, they were always linear expressions with respect to the decision variables. And this is the week that changes. This week, we're going to add a little bit of a twist to it and say, okay, what happens if there is some sort of nonlinearity that I must impose on an objective function area or a constraint there? What happens to the model? What happens to the computational complexity of that? And so that's kind of what we'll start looking around at tonight. And so in the textbook, we'll be in chapter 8, nonlinear optimization models. I've already got my Docker container up and running there. So just to make sure everybody knows where we're at there. If you're going from the root of that Docker container, you'll see the lecture folder. Inside of lecture, we are now outside of the linear programming, and now we're in nonlinear. That just has the single folder in there. And you have the chapter 8 text notes, which is what you're seeing here to the right. A little bit of background in this. You see this archive folder right here, and there's a chapter 8 tech notes with underscore scipy. And so that's been a little bit of an evolution of when I've taught this class, just to introduce the idea of scipy. Scipy is a Python package. As you can see here, it is meant for scientific Python computations, if you will. It's got a whole lot of interesting items in there, but I used to use it for nonlinear optimization, essentially. They've got nonlinear solvers there, so basically I would go in here and use it in their docs to actually do their solver. And I didn't really like that, just because in one sense you're learning a whole new Python package. That's a good thing and a bad thing, both there. It kind of has pros and cons, if you will. But it kind of disrupted the normal flow of what we were thinking about. Because a lot of times I've been talking about it in terms of the Python space and using Pyomo, this algebraic modeling language that sat on top of solvers. And I wanted to keep that consistent trend there. So I think this will be the second or third lecture or third semester that instead of using scipy, I've used IPOPT, pronounced IPOPT. IPOPT is the solver interior point optimizer, is kind of what that stands for, if you will. And so one of the things that I've done to help facilitate this class is basically up to this point in the semester, we've been using GLPK as the solver, and that cannot do nonlinear problems, as far as that's just one of the things that's a limitation of that solver, is that it has to be linear in nature. So obviously in a chapter entitled nonlinear optimization, we have to change the solver. And so what I've done is I have installed into this Python container inside of the image the necessary items to have IPOPT, excuse me. And so that's built in here. And so where that allows us to continue using the Pyomo algebraic modeling package. And then at the bottom where we say, hey, we want to create a solver, we'll just point to IPOPT instead of the GLPK there. And so it's a little bit of background as far as what's happening, why there's the archive folder there. That's because of the previous teaching with scipy. Now that changed to continue the use of the Pyomo modeling language, and then just a different solver underneath it there. So a little bit of the technical background of what's going on here. But overall, for what we're going to talk about tonight, you don't need to get too worried about the weeds that I just described there. All right, so with that being said, I'm going to go ahead and restart my kernel and run all the cells here just to give us a clean slate to work from. All right, so that should turn to a 1 here in a second, and it'll be off and going. There we go. All right, so setting the stage a little bit here. As you could expect, not every problem is perfectly linear as far as when I'm going to take a business problem or take some phenomena and I'm trying to create a mathematical model of it. Probably the first thing I would try to do is try to frame it in such a way that everything is linear, just because that's an easier thing to develop, easier thing to solve for the solvers. And so if I can create a model that is linear, I would probably do it that way. But sometimes when you start looking at that, you're saying, okay, if I make this constraint or make this objective function linear, that is breaking the actual phenomena, the actual process too much. And what I mean by that is, I think I show a slide early on in the semester that basically says that all models are wrong, but some are useful. As a famous statistician, I think back in week 1 we discussed that idea. And so it becomes, okay, is this model wrong enough then by forcing something to be linear that's really not linear that it becomes no longer useful? And so let's say that for the night that is the case, that there are going to be places where I cannot force it to be linear, and so I have to embrace this nonlinearity. And there are different ways you can even attack this. One thing that we won't talk about tonight, but it's one way, is to make something piecewise linear. By that, you basically have a nonlinear function, we'll say, and you approximate it with a piecewise defined linear function itself there. So it's got basically a bunch of straight line segments that are approximating the nonlinear arc, if you will. And then you can basically use a linear solver to solve those. But we're not going to look at that. We're going to actually look at the true nonlinear solvers themselves there. And so a few business applications where this may be, marginal product cost, depending on the volume produced. And now all of a sudden, the cost of a given unit depends on how many units I make, right? I think of that in terms of like learning curve type behavior in a production facility, as far as, okay, if I make 10 items versus I make 100 units, will the operators, if they're actual physical people out there putting things together, are they going to become more efficient at the 100th one versus the one at the 10th, if they've never seen the product, especially before, and they're having to figure things out on the fly, so to speak? That may be a case where we have some nonlinearity in there. Demand between product and price, and that's one thing that we'll look at very shortly here in our first extension of this golf bag problem that we talked about a while back. But typically, that is something that we have to have in our minds, right? The higher something costs, the less people are going to be able to afford it, and there's going to be some relationship with the demand itself there. And then I would assume most of us are somewhat youngish adults, if you will, and so the idea of compound interest is something you possibly have looked at before. You may have computed your amortization schedules on like a car loan or something like that, and just shown, okay, over the life of the loan, how much is it going to cost, depending if I go with this loan, with this down payment and that interest rate for that duration, or if I started making early payments on it, how does that affect things, right? If you ever looked at those type of computations, those are essentially nonlinear at that point as well. And so hopefully that gets us thinking in the stage of, okay, this idea of nonlinearity does exist. I need to be able to have some tooling around you, right? That's one of the things I try to talk about this class. I'm trying to give you tools in your analytical tool belt to basically be out there and be prepared to face some problems. And so hopefully by the end of the night, you have some tooling for the nonlinear problems that you will inevitably see at some point in your career. All right, so with that being said, let's go ahead and slide down and make things a little more tangible. So back in chapter 2, way back when, one of the first linear programming models that we solved looked like this right here. It was a golf bag problem. There was only 2 types of golf bags we made, standard and deluxe, right? They had some operations that these golf bags had to go through, or departments, where every golf bag took so much time out of individual departments, and each department had a total capacity. During that, we also simplified it and said things like, okay, each type of golf bag, the standard and deluxe, had a certain profit contribution. Okay, that's all it was. And then for chapter 2, we basically formulated this linear programming model down here. And that was great back in chapter 2. That's exactly what we wanted to get you used to the idea of objective functions, decision variables, constraints. But tonight we move forward a little bit. more. And do remember that in this, X of S and X of D were the amount of bags to produce of the standard and deluxe bag. And the way we're going to move forward tonight is just this whole idea that the demand may be influenced by the price of the bag. And so in these earlier problems, we basically said things like, well, the market is so much in demand that as many as you can make, they'll always be sold. You're guaranteed to sell everything that you make. So basically the idea is, okay, how do I make the most as possible in terms of, and I really should say that a little bit differently, right? Not make as most as possible, generate the most profit as possible, and determining what I need to make to do that. That's essentially what we did in that week. So now we introduce this new condition, and it says, okay, what if there is a relationship between the price and the demand? And it looks like this. So the X of S, the amount that we're going to produce, is equal to 2250 minus 15 times the price of the standard bag. And a similar relationship with the deluxe bag. The number of deluxe bags we're going to produce is equal to 1500 minus 5 times the price of the deluxe bag. So what this does is it starts to mess with our objective function, our expression for the profits. And we need a little more information because obviously this is going to affect the number we want to produce and it's influenced by the price. Well, to calculate profit, what is it? It's revenue minus cost. Everything up here, we're talking about revenue and we need to know some costs. And just to simplify things, we'll say, okay, the costs of the bags are static, they're constant. For every standard bag or $70 worth of cost, and for every deluxe bag, there's $150 worth of cost. Now, the same idea still holds that we want to maximize the overall profit, but now we have to do some work, right? Because this simple objective function here is no longer valid. So let's dive into this a little bit and see if we can come up with a new objective function, really is the first part of our conversation. So I'll get my whiteboard set up here on the left. And start our process for the night, golf bags. All right, so we need to be thinking about these relationships. So like if I look at just the standard bags, we'll know that P sub S, this represents the price of the bag, the sell price. So the price of the bag, and X sub S is the demand of the standard bag. And they're related, right? The relationship here that is given is X sub S is equal to 2250 minus 15 P sub S. All right, so these things are no longer independent. They follow this relationship. It appears to be linear between the two of them. And so we need to determine a way to compute the overall profit contribution for the standard bags, right? That's still a requirement for our objective function. Well, if we think about that, well, we would have some sort of revenue computation. And the revenue would be X sub S times P sub S. But X sub S looks like this. So one of the ways I can think of that is, okay, if I just take this and solve for P sub S, I would end up with what? I would have 2250 minus X sub S all over 15. And then I would say something like the revenue is P sub S times X sub S, right? This is the amount of the sell price of the standard bag. That's how many standard bags that are going to be demanded and will in turn produce. Well, now that I've got these expressions, I probably could have just put it as X sub S right here and got the same, but well, same relationship here, but we'll keep going the way we are. We'd have 2250 minus X sub S over 15 times X sub S. And hopefully at this point, is where you're starting to see some issues, right? If this revenue component is going to be part of my objective function, all of a sudden I'm going to have a nonlinear term with my decision variables, right? The decision variable here is x of s, and I'm seeing, if I look at this, a negative 1/15 x of s squared right here, right? There's an x of s term that's going to fall out of there, plus some value here times x of s. So I don't have that off the top of my head. We'll go to Excel here just to do a little arithmetic. 2250 over 15 is what I'm looking for. $150 plus 150 x sub s. All right, so what does this tell me? This is the revenue contribution for P sub s, or excuse me, for P sub s for the standard bags. Well, I could also figure out the cost, right? The cost of these standard bags would include this down here, right? The $70. So if I wanted to do that, I would just say, okay, the cost here is going to be the $70 times, and it appears I've got a situation with the battery here. So do give me one moment here, just to make sure that we don't end up with an issue. Oh, let me see. Sorry, my charger got unplugged here. It appears that the battery is now plugged in. And yes, we're charging up, okay? So good deal. So sorry about that. All right, where were we? So we had a cost of 70 times x of s, right? That's the total cost associated with the production of standard bags. All right, so that's good. And we basically need to do this same logic for the deluxe bags real quick. So we'll have the same idea, except we'll have P sub D and X sub D, and then the revenue here. Well, let's do the same idea here. We'll have P sub D, just using this expression here, is what 1500 minus X sub D over 5. And the revenue is P sub D times X sub D. So we would have here the 1500 minus X sub D over 5 times X sub D. So I'm seeing negative 1/5 X sub D squared. 1500 divided by 5 is 300, I believe. So plus 300 X sub D. All right, so now that we have that, we could still say our cost on this side is now 150 X sub D, right? Unit cost times the amount that I'm going to make. And at this point, the kicker is now I can just combine these, right? If I combine all the information here and here into a total expression for profit, it would be all of the revenue. So that would be something like negative 1/15 X sub S squared plus 150 X sub S. Then this term would be also revenue minus 1/5 X sub D squared plus 300 X sub D minus 70x of s minus 150x of d. So if I kind of label this a little bit, I've got between here and here, this is revenue. Standard bags here, deluxe here. And then from there to there, I'm subtracting off cost. And it looks like I could clean up some terms here, right? I've got some squared terms, but then also I've got a couple cases where I've got these kind of linear terms with respect to each decision variable. So I'll go ahead and write that once more time. Negative 150 x of s squared. I've got positive 150 minus 70, so that's plus 80 x of s minus 1/5 x of d squared plus 150 x of d. And the kicker here is that this right here now is our new objective function. Because our objective is to maximize the overall profit. Well, now we have taken into consideration this dependency of the price and the demand, derived a new profit expression, and now we step back and say, well, okay, the profit expression is nice in the fact that it's a function of the two decision variables we already said, right? The x of s and x of d, but now we have these squared terms in them, right? Right here and right there. That is causing us to have nonlinearity in the model. So everything that we've done up to this point in the semester, as far as solving wise, falls apart because the GLPK solver can't handle this. So now what do? Do we just throw up our arms? Well, of course not. We need to go about solving this thing. So just to make sure we end up in a good spot, we did. And a couple notes about this as far as, yes, there's some nonlinearities here, but one of the things we'll talk about through the night is basically that not every nonlinear expression or function is created equally, we'll say. Some are computationally more difficult than others. And for instance, the very last problem we solved tonight, there will be some complications associated with that that aren't in the other ones that we'll solve for this evening. In this case, this is just a polynomial. It's got two variables in it. They're two independent variables, but it is a polynomial. The highest term is squared term, so it ends up being quadratic. And that's really one of the easier ones to solve. And so that's how we'll attack this one tonight, is under the idea that, okay, yes, it's quadratic. In this case, it falls either convex or concave. We'll talk about those terms here in a little bit. And so we know just simple hill climbing mechanisms will lead us to the correct result there. And so one of the things we would possibly want to do as kind of the teaching part of the conversation is, okay, yes, we do have these constraints in our original model. Here, these still hold, right? No matter what this objective function does as far as the relationship between price and demand. But we still have these physical limitations at the department's level as far as they have only so much time associated with them. But let's first ignore all that. Let's ignore any of these constraints and say, okay, let's solve this for its maximum profit with respect to x of s and x of d, something you may have done in like a multivariable calculus class, essentially at that point. And maybe it helps sometimes to graph these things, and so that's what I'm doing here as far as it's a function that's in 3 dimensions, right? 2 independent variables in 1/3 dimension, so it sets up to be graphed fairly nicely. And so I can just take some values for x of s and x of y, x of d, and then plot them. And so you would end up with a shape about like that. And you might say, well, okay, if I could plot something like that, I guess I could just kind of like say, okay, the top of that curve, this z-axis is going to be the profit. So the top will be somewhere right in here. And you can kind of do by inspection, if you will, and figure out close to where the optimal decision variables would be and what the resulting objective function is. But of course, we would like to do a little bit better than that. And so this is where this IP-OPT solver is going to come to play. And I'll just go ahead and start off in Python tonight, and then we'll also bounce back and forth in Excel as usual. So the nice thing about using IP-opt is that, again, it keeps all of the modeling work that we've been doing up to the semester in Pyomo the same for the most part. You'll obviously have different expressions. You'll have some nonlinear terms there, but you're going to express those in the same way that you have been. And then we'll just change out the solver. So to kind of reinforce that, I'll just create a concrete model of Pyomo like I have been doing. M.x sub s will be a variable for us. Again, it'll be non-negative reals. Same thing we've done before. M.xb, another variable, again, the domain of pe.non-negative reals. And now we can already get to the objective. So I'm just going to say this objective, obj, is equal to what? Negative 1/15 times m.x sub s squared plus 150 times m.x sub s. Oh, going down one, plus 80 times m.x sub s minus 1/5 times m.x sub d squared plus 150 times m.x sub d. And then I'll set the property on my model of m.obj is equal to a pe.objective. Expression equals obj, and the sense is equal to pe.maximize. All right, so I guess just a sanity check here. We could say m.prettyprint. And I have this right here. Okay, it does say that I got two decision variables. That's great. The expression for the objective function, that looks reasonably good as well. And so basically it gives me confidence, okay, the model is what I wanted to know. And now we need to create a solver. And usually we would have said GLPK here. And just to show that this won't work, I'll say results equals solver.solve the model. Well, t equals true. And let's see what happens. Uh-oh, we got an exception. Aha. Value error model objective OBJ contains nonlinear terms that cannot be written to the LP format. So this is what we're saying, okay, something went wrong as far as this model is expressing a linear objective, and now the objective has nonlinear terms there. But do not be too alarmed. We will now switch GLPK to IP opt. And almost immediately what happens, we've got some nice report out to the Jupyter notebook. We've got some kind of metadata type stuff of what this thing's actually doing inside. We won't really get too hung up on that tonight. We'll basically, we'll always think of that as a black box, but just some considerations to be made about the solving process. And then look, it exit with an optimal solution. Good job. And so we can display the model because, again, Pyomo basically takes and stuffs those optimal solution values back into the different attributes of the model. And while we can see that, okay, the number of standard bags for this unconstrained problem should be 600. The number of deluxe bags should be basically 375. And that would generate or yield a profit of $52,125. So that's a great place to start, right? We basically solved the nonlinear expression, and basically we now have a result to work with. The key thing to note here is that's a result, and we haven't considered any of the constraints that are tied into it. So that is that part. And not to stray too far from Excel, since we've already got it open, just to show you how that would also be done in Excel, and to kind of show the differences to the very beginning of this lecture. I could have like decision variable cells, x of s and x of d here. And an objective here. Here I would, again, write out the expression. Now I have to reference the cells. I believe we've got that there. Actually going to be formatted to dollars, so that's good. So if I'm happy with that, you still go to data and solver as usual. Set the objective. This is all the same as before. I want to maximize, yes. There's no constraints, and this is probably the biggest part as far as usually we would have said GRG nonlinear and changed to simplex LP, but now we are going to leave it for GRG nonlinear for the majority of the night there. So if I just solve this, it has converged to current solution. All constraints are satisfied. Well, there wasn't any constraints, so that wasn't terribly bad. And looky here, we basically have the same results on both of them. Basically, X of S right at 600, X of D right at 375, resulting in a profit of 52,125 there. So there's subtle differences, right, at the end of both of those solution processes, basically flipping around on the solvers a little bit there at the end for this nicely behaving problem. So I guess I'll take a breath here. We've been going for a little bit. Any questions or concerns at this point? Okay.
I'm good.
Oh, you're good?
Yeah, yes.
All right, very good. We'll continue on. So, okay, if we're good at this point, as far as, okay, yes, I understand the nonlinear part of the problem. I understand the slight tweaks and solutions. Let's go back and say, okay, this isn't really good in terms of the solving of the original problem, right? Because basically, at this point, we've thrown out all the constraints and just said, okay, imagine they don't exist and go solve the model. But inevitably, they do exist, right? So we need to return to those constraints. And really, that's not too big of a deal. So there's page down through here. And before I get into that, basically not too big of a deal, because basically what we're going to do is just interject this objective function with these constraints, and we'll need to solve this combined problem. Before I get to that, though, I do want to make sure that we talk about hill climb a little bit. And so what I've done here is gave us a small example using the same problem here. And so what this is a secondary Jupyter notebook, and it basically just talks about these gradient descent or gradient ascent type of algorithms there. And so for this problem, we saw that shape of that function when we plotted it was kind of like an upside down umbrella, if you will, kind of looked like this. I might need to run all the cells so that blows out a little bigger. There we go. We saw that it basically looked like that as far as just kind of this upside down, nice smooth hill essentially. And those are nice because you can basically write these gradient descent type of algorithms, and they'll slowly climb up the top and be able to terminate at that peak, if you will, in the terms of a maximization problem. If you're interested in a little bit of like, okay, what does that mean to do that as far as a gradient descent type of algorithm? That's what this notebook is for essentially. So basically, not to dive too much into this because it gets into a little bit of the calculus stuff, which we don't dwell on too much in this class, but you basically start with your objective function that we just did, and we think of that as a multi-variable function. In this case, just two variables, x of s and x of d is equal to that. And back to your bit of calculus, if you've had it, this in PSU's undergraduate would fall probably in the Calc 3 area, is you basically take partial derivatives with respect to each one of our independent variables, i.e. our decision variables today. And you end up with these expressions here. And what you want to do is you use those partial derivatives to develop the gradient, which looks like this right here. So you have the partial derivative of the function with respect to x of s times the unit vector pointing in the direction of x of s. Same thing with x of d there. Now that you have the gradient, basically, this is talking about the direction that at any given point on the surface is the direction of highest ascent or highest descent, depending on which way we look at it there. And knowing that, basically, you can throw yourself at any point and say, okay, from that point, start climbing, and it'll climb to the top of the hill, so to speak. And that's basically what this logic is down here. First, in a very simple formula, where basically you start at some place, you're going to the next place. How do you do it? Basically, you look at the gradient and you take some step size h in the direction of the gradient itself there. And so that's what we're doing at this point. This does lead to some very interesting types of problems as far as if I've got a gradient step size, how do I know that I'm going to terminate at the correct spot there? And so you might hear terms like simulated annealing, which is basically where this idea that the step size starts out at a larger value, and then as I walk down this search path, the step size becomes smaller and smaller. Where does it come with the idea of simulated annealing? Where does that term come from? Well, that actually comes from the ideas from like the foundry area, where I basically heat up a piece of metal to a very hot temperature. Think of the atoms in that metal bouncing around very quickly. They have a lot of energy because of that hot temperature. And then as it cools, the atoms become slower and slower, so to speak, right? They start bouncing around a little bit less, so on and so forth there. And so that's kind of the mimicking of this annealing process there. What that looks like visually after I run this, you can see I ran a loop here. You can kind of study the Python code if you want. That basically terminated after 173 steps. And as I stepped through it, it basically went on that red trajectory there. And so notice here, I basically start way down here at just some random value that I happen to pick, and then it climbs here. Why did it climb in that path? Because it was following the highest, it was following the direction of the highest ascent, the steepest uphill part, if you will, at any given point. And notice it kind of wanders its way up to an approximation of that maximum value. Looks like here that maximum is right about 600 and 350 with 52K for the solution. And that should mimic what we solved over here. Yeah, 300, 375, 600, 375, and 52, 125. So we're definitely in the neighborhood of that value there. And so, again, a little bit of thought as far as what that actually looks like. And if you want to, you can dig a little bit deeper in that hill climbing, but that's kind of a secondary thing for the class. Don't feel like you have to understand that fully for what we're doing the rest of the evening. All right, so before we made that little tangent, basically the idea was, okay, I've got to be able to now interject those constraints, right? Everything we've talked about with this problem before was just with the objective function and isolating that, basically solving it in a vacuum. And now we come back to that and say, okay, now that we've solved it in a vacuum, that kind of can be thought of as an upper bound associated with the possibilities of the solution for this problem. Now we need to interject those constraints back. In these cases, we're talking about limitations of the amount of hours that is available in any given department here. And so that's what you're seeing down here. And you can look at this in a graphical sense, right, as well. So I could plot this with x of s and x of b. It's got two decision variables. We can kind of return back to those graphical roots back in chapter 2. We would still have to define the feasible region. Well, that's what we did here. Remember, that's only based off the constraints. But now what if we throw a dart out there and say, okay, we'd already solved for an optimal solution, 600, 375, right? That was just by looking at the objective function. Let's just see where it lands, right? If that happens to land inside of the feasible region, then we're done. We're good to go. But not surprisingly, at this point, that is not in the feasible region, right? It's way off here. So it violates the constraints and it's no longer a feasible solution, i.e. it can't be an optimal solution for this problem there. So what did we do last time that we were at the graphical solution steps back in chapter 2? What did we do? We started picking values for the objective function and plotting those and seeing how those interacted with the feasible region. Back in chapter 2, everything was linear, so those were nice straight line segments. Now that we're in the nonlinear realm, we're not going to be having nice straight line segments. In this case, we're actually going to be having ellipses. And so we've got some code here that basically draws the ellipses. And we end up with something like this. So now that's the same feasible region, that red dot's the same spot. But now what I've done is I've started to say the overall profit's going to be less and less. And what's happened here is I said that less and less, the radius, the radii, the max and min radii, or the major and minor radii of that ellipse has grown each time I've said that. And so then I can start looking at that and saying, okay, where does that intersect the feasible region? And it looks like it's going to somewhere right in here, right? At some point, this arc will just kind of kiss that line segment there, and that will be our optimal solution. And I guess you could do it graphically, like just from inspection right now. I know it's going to lie somewhere between 50,000 and 49,500 there is between one of those two. And I could jump the step size down, right? I could do it every 100 units, every 50 units, so on and so forth, or $50, and try to figure out that exact spot there with inspection. But one of the key things to take away here from this and how it's different than what we've done so far is that notice that's going to hit somewhere on the middle of that line segment. And that's very different than what the simplex algorithm was telling us with the pure linear programming stuff with real decision variables that we started the semester off with, right? With that simplex algorithm, real decision variables, we were guaranteed that the optimal solution was going to occur at a vertex of the feasible region. And so that was very nice. It decreased the amount of complexity in the search process for that optimal solution. Now, all of a sudden, we have the ability that the optimal solution could occur somewhere on the boundary of the feasible region, right? Which is going to happen here in between these vertices. So it's going to hit somewhere in there. Or even more, that point could have been inside the feasible region, right? And that could have also been an optimal solution there. So hopefully you're starting to see, okay, yeah, this is a different type of problem. So we need different type of algorithms or different type of solution paths to tackle it there. Don't worry, I will not ask you to do anything graphical here for the homework sets and whatnot. All right, so make sure we don't have anything here. Yes, we're all good. So now we need to turn to the computer solution to this. And really the computer solution to this one is not terribly bad as far as that goes, because I can do the same stuff that I've used to been doing. If I look at the Python code over here, I'm just going to take this section of code, reuse it down here. I've still got my objective function. Well, in the Pyomo code, I can still write out very similar constraints. I'll just say m.department1 because I don't remember the departments there, but I can just say pe.constraint, an expression 0.7 times m.x_s plus m.x of d less than or equal to 630. Great, m.department2. Department 3. And department 4. All right. And it looks like I had a misspelling. There we go. If I look at the model itself here, everything from here above, that was all the same as before. All we've done is add the same linear set of constraints that we would have done if this was a fully linear problem. We've already defined the solver, so I can just say again, results equal solver.solve model, seeing out the results here. Very quickly, it comes to a solution. Notice saying it's the optimal solution has been found. And we'll display the model here. Now, this is the optimal solution now with the constraints being applied. And so notice we have a smaller objective function, which is something we expected, right? We were just kind of looking at the results from our graphical solution over here just a little bit ago. And we were saying, okay, it's between the purple and the green, somewhere between 50,000 and 49,500. So with that in mind, giving us a little context, this value seems very plausible, right? 49,920. And then the optimal solution for the decision variables, 459.7 and 308.2 there, assuming that they're allowed to be real numbers. So hopefully you're saying, okay, yeah, that overall process is exactly the same as what I'm used to as far as using PyMO to model it out. I won't go ahead and do this one fully again, in Excel, but in Excel, you would do the same thing. You create your block of constraints here exactly the way you would before. You would have still gotten the solver dialog box and entered them here as usual, just left it at GRG nonlinear, and you would have ended up with a similar solution there. Do this then. All right. Make sure that we're in good shape here. And we are. So I guess, again, I'll pause, take a break, take a sip of water, and see if there's any questions, concerns with how we've now added back those constraints. And now we're at an optimal solution that actually makes sense with respect to the actual physical process.
I am fine.
Okay, very good. All right, so now that we've got that in place, we've kind of set the stage. We've been able to solve a simple problem with a nonlinear objective function. We need to introduce a little bit of vocabulary with this next bit. And so I've tried to impose on you up to this point that yes, things are more complex with nonlinear problems. Part of the more complexity is that the idea that you can have different variations of optima. And optima, when I say that, it could be a hill in the case of a maximization problem, or can think of it as a valley in the case of a minimization problem. And so that's where we have to differentiate between these types of optimum, not just if we're like at a hill or a value or a valley, but just basically the magnitude of it. And we'll talk about that in terms of, is it a local optimum or is it a global optimum? And a local optimum, basically what it says is that you're the best candidate in the neighborhood that you're in the local neighborhood, if you will. Just all your neighbors are inferior to you in some way. And so when I say inferior there, it depends on the sense of the objective function. And so if I'm talking about a maximization problem, I'm basically sitting at a point that is higher than any of the neighboring points immediately around it. If I'm talking about a minimization problem, I'm talking about a point that is lower than any of the points that are immediately around them. And when I say higher and lower, I'm talking about the resulting value of the objective function. So notice here, I'm trying to emphasize the idea that local is basically talking about the immediate area around you. That is different than what we're typically after, which is the global optimum. The global optimum just says, okay, out of the entire space that I'm possibly able to look at, you are the best candidate solution. And so again, that means, okay, if I'm looking at a maximization problem, that this is the highest peak out of the entire search space. Minimization part, this is the lowest valley out of any of the search space that I have to look through. And so that's really what we're after. And the key things to think about that is you have to be careful because there are the possibility that some of these solvers, specifically the one that I talked about a little bit earlier, the gradient ascent, ascent problems, is that some of those solvers can fall victim to the local optimization problem there. And so what I mean by that is basically that gradient ascent solver is going to pick some spot randomly on the search space, we'll say, and start climbing up, right? Well, it could be possible that it's going to climb up to a local optimum and not the global optimum. So basically, in my mind, what I usually think about is I'm putting it out in space, it's climbing up some anthill and saying, wow, I'm at the optimum. I'm looking all around me right in the immediate area, and it says I'm higher than anybody else. Whereas just a few spaces away from it is the start of a mountain. And so You're nowhere near the top of it, but the solver isn't intelligent enough to know to jump, if you will, from the anthill to the foothills of the mountain and climb up there, right? And so again, hopefully that kind of gives you a little bit of a visual indicator of what could potentially happen with these problems. And so you're saying, wow, okay, that's a dangerous thing. How do I combat that? And we'll talk about strategies below. But some of the things you wanted to look at is the nature of the problems themselves. They're the nature of the nonlinearities, because I've said before that not all those are going to be equal in nature. And some of them are nicely shaped, like the one we just looked at, it had that kind of bowl shape, right? It's nice when they have those nice smooth bowl shapes, because we know that in the gradient ascent type problems, it doesn't matter where I pick on the plane. Maybe it'll take me longer to get there, but I'm going to get to the top, the global top, if you will, the global maximum. And so that's where we interject these idea of concave and convex functions. Concave functions, this is the bowl shape down. The way I would talk about this would be the same way I talk to my little kids, as far as, okay, that would be as if I took the cereal bowl that I'm used to eating out of in the morning and I turn it upside down, right? So it's kind of the bowl shape down. Think of it the way you hold an umbrella in the rain, essentially. And the nice thing about that is that there's one local maximum, but it's also the global maximum there. And hopefully that gives you a mental image of what it looks like. Well, how do you take that to the algebraic expression of it, essentially? And so here's the things to look for, as far as, okay, there are squared terms, i.e. it's a quadratic function. Those squared terms have negative coefficients, and there's no cross product terms. An example would be something like this: negative x squared minus y squared. No cross product terms basically say there's no x times y in there. The other side of things, as far as, okay, I take that cereal bowl, I flip it right side up, so to speak, that I would be able to put the milk and cereal in it. And now it's a convex function. Now that we know that the local minimum is also the global minimum down there. And it has very similar terms, right? You've got squared terms, which makes it quadratic, and those squared terms have the positive coefficients, and there's again no cross products, so you'd have something that looks like that. So if I looked at these, you would have something that would look very nice like this, right? Think of being able to walk up that hill and you wouldn't have any surprises in any way, shape, or form, so that's good. And think of this right here as another one. Here I now have a bowl. If I was to walk down the hill, so to speak, again, no surprise, right? You'd always end up somewhere down there at the bottom. So these, again, are nice in the terms of, yes, they are nonlinear. They're a little bit more complex, but they're not too scary, right? And hopefully you'll agree with me there. Unfortunately, not all functions are made like that, though, right? Lindu is another type of solver there. I grabbed that nice function down there from their API manual itself there. Just by looking at it, hopefully that looks nasty, right? I see some exponentials in there. I have only two independent variables, so that's nice, but it's hairy, right? If you were to plot that, you would end up with something that looks about like this. And they've obviously engineered that function to behave or be shaped in a certain way. And let's talk about this for a little bit. And what are the challenges of it? And I'm thinking of the challenges more from like a gradient ascent type of algorithm. Well, one of the things I talked about with the gradient ascent is basically, okay, I got to start somewhere. So you pick a spot in the x, y directions, like ordered pair x, comma, y, and then you start the solver. But one of the first things I'm seeing is the fact that, okay, I've got this spot here that looks very flat. That's kind of around the perimeter of this, almost looks like a square with some interesting parts in the middle. Well, if I start way out here, the gradient's not going to be really sharp, right? That is almost perfectly flat there, so that could cause an issue. And then you say, okay, that's great. Well, what if I happen to pick a point, we'll say like right in here, right? Well, this would be a case where I could get stuck at a local maximum. Because if I look right there, zoom in a little bit more, say I start at this point here, well, if I follow the method of the gradient ascent, basically it's going to climb up this hill and it's going to stop and terminate right there, right? And it's going to say, oh man, I've hit the peak. I must be at the maximum, so I'll stop looking essentially. Okay, that's great. You've found a peak, but we would call this a local maximum, not a global maximum, because we would really, if we were trying to maximize this thing, we'd be interested in this guy way up here, right? So we do have to be a little bit careful there. And there are ways to go about trying to combat that even with these type of problems. Just give you a little bit of a peek in here from the Excel side of things. If I go to data and I go to solver, now I go to the options, the GRG nonlinear. One of the things I could potentially start off with is this use multi-start with a population size and a random seed. What is that, you say? Well, basically what that is the idea of instead of starting at one spot, i.e. throwing one dart on this XY plane and then chasing up, what if I threw a lot of darts? I.e., what if I threw 100 darts here, randomly placed on there, and said, okay, from these 100 spots, go climb, right? And then keep track of which ones climbed the highest, right? So you can see how that would potentially work. Another one would potentially be this evolutionary idea. And so the evolutionary idea is very interesting. If you've heard of it before, evolutionary programming or genetic algorithms is another way to talk about this. This is another example of ways to combat that nonlinearity. Not to get too deep into it, and if you're interested, I could definitely send you a hour-long lecture from, I think Patrick Winston was the MIT professor at the time. I think he may have passed away at this point. But on the MIT OCW, they have an artificial intelligence course. One of those lectures is associated with genetic algorithms. Not too terribly deep in terms of complexity, but just shows you the appreciation of what that algorithm does. And genetic algorithms, they're built off the idea of kind of naive evolution, if you will. And so you basically have these candidates and they have fitness functions and then they go through these generations, if you will. And the whole idea is only the best candidates from each generation associated with a fitness function survive. And basically what it allows things to happen here with this idea of mutation is that not only do they start to climb, but this mutation allows them to jump, essentially. And so the idea would it would be able to essentially jump between these hills and have a better chance at getting to the global optimum. So again, things that are out there that are things that help with this nonlinear problems, things that were not necessarily needed even with the ideas of linear programming, real decision variables, and the simplex algorithm there. So with that being said, I'm hoping to just kind of encourage you to think and appreciate the complexity that's happening there and the things that would have to be considered, even though a lot of that complexity is hidden away from you in this class as far as, okay, I go through and, well, for the Python side of things, all you told me to do was exchange GLPK to IPOPT, right? That was the mechanics of it. Well, yes, that's what it is, but I'm hoping that you see the underlying issue of why you did that essentially. Similarly with Excel, essentially in one sense, all I've told you to do is, okay, leave it at GRG nonlinear instead of the simplex LP, right? Yes, but again, I want you to understand a little bit more of why that is. All right. So as we continue on in the lecture, one of the things to think about is this idea of sensitivity analysis. Well, it's chapter 3, right, of our introduction in linear programming. We got into that, range of optimality, reduced cost, range of feasibility, all that kind of good stuff associated with linear programming. And there are similar ideas in the nonlinear realm there, but they don't meet a nice one-to-one comparison exactly. And so the book does touch on a few of these things, not in great detail, but just the idea that, okay, there is this idea of a reduced gradient, and that's somewhat similar to the reduced cost. Remember, the reduced cost was this dual value associated with the non-negativity constraint on a decision variable there. Well, we also had this idea of shadow prices or dual values, right? Um, that's similar to this idea of the Lagrangian multiplier because it has to do with the rate of change of the objective function with changes in the right-hand side value. The biggest difference here is that, okay, yeah, it's very similar in nature, but for the linear problems, that dual value had a range of feasibility that allowed us to extrapolate the values up and down to see how they impact the objective function. Here, that range of feasibility is basically shrunk down to zero, essentially. So we don't have the same freedom to do that extrapolation there. All right. So the last three sections here are associated with more applications of this. And so before I get too carried away, let me go ahead and save this off. If you don't mind, I may just talk through most of the models here and solve them in Excel or Python, but not write so much of it out. It's golf bags. All right. So we'll start with a couple finance related ones and then one associated with forecasting there. Index funds. Index funds are a strategy, a mechanism, if you will, that help people invest. And the whole idea is that maybe you're not wanting to be a day trader or anything like that, but you're wanting to have your funds or have your investment perform similarly to a broader market index, right? Index would be like the NASDAQ or the S&P 500 that basically is used as a bellwether or a basically an agent that's being making closely to a broader set of stocks down below, if you will. And the overall impressive idea is, okay, I want my investment to do as good as the market because it's hard to beat the market, we'll say. And so this fits into this lecture because the ability to create that index fund can be framed as a nonlinear optimization problem. And so to do this, we'll need a little bit of data. And so that's what I'm showing you here. We've got index funds, and we're looking at the NASDAQ specifically between 2009 and 2012. I just grabbed some companies. You can see their stock tickers there. And then the year-over-year performance for 2009, 10, 11, and 12, all tidied up in this data frame here. I also have to have, okay, an index to work off of, so I'm using the NASDAQ, and it's the NASDAQ year-over-year performance here. And so the key part of this is going to be, okay, I need to tell somebody to invest their money in so many shares of these companies such that if any of these year candidates follow out for the next year, it is going to match the performance of the index or the performance of the NASDAQ index to be specific here. So hopefully you're thinking, okay, the key knobs that I have to turn is how much to invest in any given stock, right? That's the only decision I really have. And at this point, I'm not seeing any place where they're telling us a set dollar amount as far as you've got 50K, 100K to invest. And so we'll just assume it's all a fraction of a total amount that I'm going to be investing. So we'll just say, okay, I'm going to have these fractional investments, and I'll say that they must sum to 1, essentially, because that's going to be the entire amount that I have to invest. And so to do that, we first start thinking about, okay, what are the sets involved? And so in this case, our sets would be, I've got a listing of companies, and I've got a listing of years, candidate years, if you will. So I can define a set of year scenarios. It looks like I call that S. 2009, 10, 11, and 12 would go there. And then I have a set of companies or investment options, which if I'm scrolling down here, those are the I for investment. So MU, Yahoo, I think it's Buffalo Wild Wings, Netflix, and Google. Don't know if I remember MU off the top of my head. Then I've got data, and I've got data associated with this table here, as well as data associated with this row here. And so what is that? Well, I've got the year-over-year return, but notice here it's two-dimensional in nature, and so I would need a variable with two subscripts, right? One subscript to represent the company, the other subscript to represent the year. And so that's what this is right here. ASI is the year-over-year return for an investment in a given year. And then I need the value for the year-over-year return for the index itself. Notice that's just now indexed over one thing, right? Just over a year. So just one variable here, and it's indexed over the set S. Whereas the A is indexed over set S and then I. All right, moving on to decision variables. Well, the decision variables here, like we said, is just how much am I going to invest in what type of investment option or company. So it just needs to have a single index I, and that I is going to be like MU, Yahoo, Buffalo Wild Wings, Netflix, and so forth. And then we build out a model. Okay, this model is fairly simple in terms of complexity, in the sense that what am I doing? Well, here I'm using this kind of lumped variable again, this R sub S. And that R sub S, I'm defining right down here. It kind of looks like a constraint. You can model it that way. Or I could have just written all these summations up here, but that gets a little bit messy. So basically what these scenario returns are is the linear combination of the decision variables against these year-over-year outcomes for a given year. So what I'm basically taking is the decision variable for MU times 0.8519 plus the decision variable of Yahoo times 0.2466, so on and so forth. And that would be the rate of return for 2009 candidate year, or scenario return, if you will. And I need to do that for every year. And so if that is my proposed return for that scenario year, I'm basically subtracting from that the index performance for that given year. So now I've got the difference, right? And you kind of think of this from a forecasting standpoint of I've got a predictor and I've got an actual value. And if you've been around like forecasting type stuff very often, basically what a lot of times what you're thinking of there is the idea that I have a difference and I want to minimize the sum of all those differences. But you can't just take the difference of each one of those years and sum them, because, well, one, you could have some positive errors, you could have some negative errors, and they'll artificially cancel each other out. If you take the absolute value of each one, there's some issues there in terms of complexity. So one of the common ways to do it is to square all of my errors, which is what you're seeing here. So I've got like a predicted value or year scenario minus the actual. I'm squaring them and I'm summing up all the squares. So essentially, you may have heard the term sum of squared errors, right? And so we're trying to minimize that sum of squared errors there. And so that becomes our objective function. And so the idea is, okay, now we're going to minimize sum of squared errors. Hopefully that somewhat makes sense. And then subject to what? Well, we talked through this, and this first line of the constraints is really a definition for the R sub S. Well, the only other constraint that I have here is that all those decision variables have to sum to 1. They are fractions of a whole, so that does make sense. And then finally, we say, okay, none of the decision variables can be negative as well. Okay, so hopefully that makes sense to us. Also, if you stared at this long enough, you would see that this is a nicely behaved model itself in terms of it will look like this, so it is convex. And we can think of that as nice in terms of any sort of hill climbing mechanism, or in this case, hill downward seeking mechanism, hill falling mechanism, if well, a descent instead of an ascent, will naturally find the objective, the global minimum here. All right, so if that is our model, here's our data. I've been bouncing back and forth a little bit tonight, so let's try to do this one in Pyomo. That's going to require a little bit of work on the Panda side, and then we'll finish out with some Excel stuff as well. To import pandas. All right, just bring the data over for us here. There we go. So we've got a data frame called stocks underscore DF, and we have another data frame called index underscore DF there. So either way, I got to start with our concrete model. The name we'll just say is index fund. And here, I really want to start off with some sets. So on a data frame, I can say something like, give me the index. That's this darker column here off to the left. And I can say form a list out of that. So if I can do that, now I've got those list of strings. I'll say m dot funds, stocks. We'll spell stocks. And we'll say it's PE dot set, initialized to this right here. Now the model knows that I've got some sets. Similarly, you can ask about the columns of a data frame, and I can get the years that way. That's these column headers here, essentially, is what it's telling me, and that's exactly what I want. So all right, and I could also do a sanity check of myself as far as, okay, does it know about the years? Does it know about the stocks? Yes, for both, so very good. Now we have some parameters, right? We've got the year return and we've got the index return. So let's say the stock return, I guess would be the best way to describe that, the return of the stock in a given year. The param there, we need to have an index at this point. So let's do it off the years and then off of the stocks. And I do need to initialize this as well, don't I? Yes. And so that's going to be all this information built up in here. So let's play with that a little bit. That'll give me a list here, so that's not quite what I want. That just gives me the values. That isn't quite what I want here. So we may have to do a little bit more pandas work than I really want to get into tonight here. The index returns here. Okay, yes. We don't necessarily formulate an index necessarily for us. We can do this without that, and I'll do that a little bit differently. So we'll leave that out, but we do need to have the index returns as well. What I'm kind of hedging at here is not every time you have to necessarily make the model know about the sets themselves or the parameters. You can just hard code those later on into the into the constraints and the objective function here. It's a little bit of an optional thing there. So we'll see how that can work here. IDX index returns. That's based off the years, so I will put that in there. And they typically are initialized with a list. Well, basically the same dictionary that you're seeing here. So now I know the index returns, and for that year, I know this value. All right, so far so good. Now we need to know something about the decision variables, right? M.x will say, that's a PE.var. It's indexed off of the stocks, and the domain is PE.non-negative reals. Very good. So the probably the hardest thing here is the objective to write. And so we'll look at this as the objective right here. Well, I'm summing over the set of years here. So I'd say, okay, for year in m.years, I'm going to keep a running sum together here. But to do that, I have to get the year return or the scenario return here. And so now I'm starting to take advantage of this right here, this R sub S definition. And so it is a sum. That's where this sum is here. Sum over what? It's a sum over the investment options. So I'll say sum over for S and M dot stocks here. That's over the investment options. What do I have here? Well, it's the decision variable times what? What goes here? Well, it's times this a sub I comma s. How am I going to get a sub I comma s after all this stuff? Well, this was where you have to know a little bit about data frames and how they work, probably the easiest way. Notice I can pick in square brackets now a year, and that'll isolate a panda series or a column. And then after that, I can pick on a company, and that'll actually isolate the value itself there. So I'm basically saying, okay, give me a column, and then in that column, give me a row, if you will. Well, if I can do that, at this point right here, I know both a year and a stock. So I can say stocks underscore DF, first the year, then the stock. That gets me the year return. The other thing I now have, so that's essentially this year return is like me calculating that R right there. I still have to have the M sub S. So I'll just say the index return. Well, that's what M dot index returns sub year. And then I need to compute the difference squared and add it. So I'd say OBJ plus equals the year return minus the index return. But I want to square that before I add it and keep that running total. So as long as there's no syntax issues, that should keep a running total for me, always putting in the OBJ variable. And so I need to add that back to the model. So on the model itself, I create a property objective of type objective. The expression is OBJ in the sense is PE.minimize. Hit shift enter here, it's solved without any errors. And then I end up with something that looks about like this. And so let's look and just see if this has the right pattern, right? Well, here I'm seeing a grouping, and I've got a linear combination of the investment times the rate of return up to there, and then I subtracted off the index rate of return and I squared it, right? So I've got R, capital R for a given year is there, minus that M sub S, if I look at over here, I'm taking the difference of all that and squaring, and I'm doing that for every year. So that looks plausible for me. All right, so if I go back to my model over here, I've done this. As part of doing that, I defined these. And so now I'm down to here. A very simple constraint just to say to make sure all of my variables sum to 1. I'll say unity for the name is p.constraint. The expression is a sum for s and m.stocks, m.x sub s. That's the sum. And we say that has to equal 1. Evaluate the pretty print, and we should have that now down here. Lower bound's 1, upper bound is 1. All my decision variables here in the body. Very good. All right, so now we can actually solve this thing. So I've already got the solver defined from above, and it's still going to use the IPOPT, so that's good. So you say again, solve the model, t it out with the true, with the results, in case we ever want to look at those. Solves quite nicely. Optimal solution is still found. Very good. And we'll display at this point. All right, so what is this telling us? Well, this objective here, this is the sum of the squared differences, so it's a little bit harder to interpret. But the biggest thing here is it's telling us the distribution of how best to distribute the funds across those stocks. In this case, Google, for instance, you can see that's times 10 to the negative 7, so that's basically a 0. And it's saying, okay, take about 15% and put it in Buffalo Wild Wings, about 5.8% in MU, Netflix is 7%, and most of it you can see is down here in Yahoo at 72% there. So let's make sure we ended up at a good spot. Yeah, it looks like it. And so again, the whole idea of this index fund is now that we've been able to come up with this distribution, our investment, our portfolio should mimic what the NASDAQ is going to mimic, assuming that the NASDAQ is going to behave similarly to the way it did in one of the years that we had defined in those year candidates, the 2009 through 2012 year range. I guess just to take a peek, I've got the save solutions also over here. No, they're here for us. Similar to what we've done in the past as far as set up the data. There's the sum of differences. Here's these return candidates that I'm just creating. Linear or some products, linear combinations here, and then summing them all to one. So really not much different. And then just like before, the solver, everything the same here, except for leaving that at GRG nonlinear. Again, it's nice convex. Convex, I should say concave there, I believe. Oh, convex, I was right. Convex problem there. And it nicely solves at that point to get the global minimum. So I guess again, I'll take a short little break to take a sip here and ask if there are any questions, concerns.
I am fine, sir.
Okay. I guess I'm still doing okay as far as talking and time and everything. Are you doing okay? Do you want to just keep going and we can probably get out of here in a little bit early?
I am okay, sir.
Okay.
Like I will, uh, I will do the home, like I will do the homework, and if I get any errors, like can I email you, sir?
Oh yeah. But I'm saying I'll continue on with the lecture. I just didn't know if we need a bathroom break or anything like that.
Oh yeah, sir. Yeah. I'm okay, sir. You can continue. You could continue.
Okay, yeah. But no, yeah, I still owe you a couple more sections.
Oh, sure, sure.
Yeah. All right. So now for the last two example problems here. A Markowitz portfolio and the forecasting one. Put you off to the side. There we go. So we're in index funds, so we're in the kind of the finance area here, and then also we have the Markowitz portfolio model as well. So still remaining in that kind of overall domain of forecasting and finance, if you will. So Markowitz, you can see the full name, mean variance portfolio model. Basically, again, you're trying to create this portfolio of how you're going to invest your capital, and you're trying to balance reward and risk, essentially. And so that's a fundamental thing as far as, yes, you want to maximize the reward you'll get, then maximize the return, if you will. But typically, in order to do such things, you have to invest in a little bit more risky ventures, assets, some stocks, whatever you want to be investing there. And so there's a balancing act there, right? As far as, yes, I want more return on my investment, but I'm only willing to risk so much as well there. And so his ideas in terms of this portfolio model is some way to balance these two competing things. And so first, a couple things to get through as far as definition wise. One is the return is measured as the expected return. And again, this comes back to you. Hopefully you've had a little bit of probability or statistics area. And the expected return you can see is we still have these year scenarios. That's the R sub S, so that's similarly defined as above. But now we're assigning probabilities of those years, right? Remember, we just left that index fund problem, and nowhere in there did we say something like, well, 2009, we think that's got 20% of the way probability of happening next year. 2010 has 30%. 2011 has only 10%, right? Whenever we assign those weights, if you will, those probabilities to those year candidates or year scenarios there. Well, now we have to do that. Now we have to basically say, okay, for every one of those year scenarios, to figure out, come up with a probability that that's going to occur. And so that's what this piece of S is going to be, the probability that the year scenario occur. We're multiplying it by the year scenario's outcome. That's, again, a linear combination of those rate of returns from the investments and the decision variables, and we're summing that all up. Basically, by doing that process, you're computed the expected return from the probability standpoint. All right, so now that we've got expected return, that's how we're going to measure return on investments, or your reward, so to speak. Now we also have to look at the variance. Variance is the risk, right? Think of it from variance in terms of the definition of this standard deviation, right? How much variation that has essentially in it. And so that's calculated with this expression down here. If you look at it closely, you still have this R sub S here, but you also have rate of return, right? Basically, what is the squared difference there between the year candidate return and the expected return? And then we're multiplying again by the probability of the year itself there. And so we describe that as the variance. So with those two kind of fundamental building blocks in place, how do you construct the model? How do you wire those things together? And there's two different methods. One, you basically minimize the variance and you set some lower bound on the return. Or the other side of things is I maximize the expected return and put a constraint on the variance. Typically, say I want the variance to be no higher than this value, right? And so depending on the way you want to work it, you've got these kind of two different routes to go. And so to give us a little bit of an example here, here's the Markowitz model. Our investment mediums here are mutual funds, and so those are shown on the far left column. And each of those has a rate of return given in the table itself there. It looks like we're trying to maximize return subject to a constraint on the variance, and the constraint on the variance is right here. I want a maximum variance set to 30. And then I also want to assume each year scenario is equally likely. And so that's an easier thing here as far as each scenario is equally likely. So there's 5 scenarios. So now all of a sudden we're saying that the probability of any given year scenario happening is 1/5 or 20% there. All right, so just to again show you the model itself here and think through it. Very similar to the last one, we have two different types of things we're working with, right? Year scenarios and investment options. So I'm using the same set names as above there, S and the I's. The data looks similar as well. We still have for every investment option a rate of return for it in a given year. And so that's where this is coming from. First index here is the year scenario, the second index being the investment option. Having to create another investment or another parameter here, P sub S, based off the years to capture the probability of a year scenario occurring. Well, in this case, we said they're all equally likely right there. So this basically is just 0.2 for every S in this particular case. It could be more complex for other cases. And we've got decision variables for the investment options. So we've got investment options here, foreign stocks, intermediate term bonds, large cap, small cap, growth and value variations there. So in this case, you'd have 1, 2, 3, 4, 5, 6 different decision variables. Well, we said up above, we're trying to maximize the return. So we're maximizing R bar, which is defined right here. So that gives us the objective function. And then we also have to define R bar down here in the constraints. Well, in order to calculate R bar, you can see right here, I need R sub S. So that's where this line here is coming from. For every year in my set of scenario years, I'm calculating the linear combination of the decision variables and the return on of each investment on that year. And so that gives me the expected, or not the expected return, but the scenario return. We still have this idea that the investment unity must be made as far as we're talking about fractional bits of some sum of capital that we're going to invest, and we say those all have to sum to 1. And then we have the max allowed variance down here. So this left-hand side, that came from the definition of variance, right? If I look at that and then look at this, that is the exact same expression that I'm seeing. And I'm just saying here, okay, I'm capping that at 30. So that's where this less than or equal to 30 is coming from. So hopefully that all makes sense as far as seeing the different building blocks, as far as the definition of the variance, definition of the expected return, and how those can all be put together into a model. Again, this thing is going to be nonlinear in nature. One way to look at that appears to be right here in the variance definition, right? Because each one of those R sub S's have some decision variables inside of that. The R bar also is going to have some decision variables inside of that because they reference the R sub S internally so as well. And so we're going to end up with definitely some nonlinearities inside of that squared term. That's kind of hidden away by those decision variables. At this point, I'll just go ahead and show the Excel model, if you don't mind. Save on a little bit of my typing and we can just talk through it. And we can also talk through the Python code as well, even though I'm doing a little bit more of pandas this week, just in the way the data is structured there. So that does add another element of things to consider if you're going through the Python side of things. The pandas type stuff is not a requirement as far as pandas. You don't have to use that when you're using PyOmo and these type of modeling languages there. But it would be very convenient in terms of just the data wrangling, the data mongering, if you will, as far as having just to get the data and format the data into a format that can be used in your model. But back on Excel side of things, the first thing would be to just get all the data into Excel, which is what that represents there. Our decision variables are just our stocks, so we've got cells there. We're trying to maximize the definition of the return, which it helps to have these two side by side at this point. Well, here, all I've done is I've split out some of these out, so just easier reference. So it's just maximizing the reference to this cell. And this cell, I've got what? Here, notice here, I'm taking the scenario probability and then multiplying it by the sum of all my returns down there for every year. I'm able to do it this way just because they're uniform probabilities, right? As far as that P sub S here, if that is a constant, no matter what S I give it, then I can pull that outside of the summation, right? But if that was not, and it varied with each of the year scenarios, I'd have to keep it inside, and this would look slightly different. So there's that. Just to go back on what these are. These are just the sum products, the linear combinations of the decision variables and those year scenarios. So that gets me through here. The variance is also a building block that we would need to touch on. So that's the reference there. And really all I'm doing is following this. Again, that P sub S is going to be a constant. So I'm pulling that outside of the summation. And then I'm taking the sum of squared errors, right, is all this stuff, or sum of squared differences, if you will, not necessarily errors, of the return in that year, so that's the R sub S there, minus R bar that's there, squared, plus next year minus R bar squared, plus next year minus R bar squared, right, so on and so forth there. Here is just the investment unity here and here, and then the definition of variance, which is a very simple reference point here, and the max 30 there. So maybe the constraints are a little bit different than what we've been looking at throughout most of the semester. A lot of the semester, this table was quite big. but we're using so many of these what I call kind of lumped variables just to help simplify the expressions here, that there's not too much down here, right? So hopefully you're seeing that. As far as the solver dialog goes here, relatively straightforward. As far as the objective functions here, I'm wanting to maximize that since we are maximizing the expected return, subject to the changing of these decision variables here. So that's good. And then I don't need to really include these in here just because those are built into the definitions of what I'm doing up here. And so we don't have to really include those as constraints down here, even though I'm listing them in the constraint section. But definitely down when I get into this stack of lines here is where I start showing this is the unity one, this is my max variance one, so on and so forth there. And then just solving with the GRG nonlinear, because again, this is one that is nice bowl shaped, in this case concave in this point. Excuse me, convex in this point. I'm thinking of it incorrectly there. There's concave. Yeah, concave. I need to stop doubting myself this evening. And then we can go ahead and solve. The solve here, now this would be the expected rate of return of 10.44, which should match the Python code here, Python IPOPT. Again, we got to do a little bit of work here for the data frame, iterating the rows to create this data structure here for the return data, which is going to be mapped into that parameter there. And the year probs is mapped similarly, both of which we're trying to get to a dictionary with some key that's going to match up to the indexes and then the values associated with it. We can pass it to the solver. And here I'm just doing a little bit more, instead of just saying here m.display for it, I'm actually going to grab certain values from it and print out this nice little list here. So basically here, just showing the idea that, okay, yes, expected to return the value of the objective function, 10.45 matches on each one. And then we've got similarly the same distribution, it appears, for the investment strategy there. So hopefully that makes sense as far as just talking through the model. I would say probably the biggest thing for the Markowitz models here is just making sure that you're okay with these fundamental building blocks as far as making sure you understand the expected return, make sure you understand the variance, and then basically the problem again works out in two different ways, so you have to be careful of that. But then depending on which problem variation you're picking there, you're just kind of formatting those building blocks in a certain way in order to go one way or the other. So I guess that's kind of the discussion, if you will, that I wanted to have around the Markowitz model. Any questions, concerns on your part?
I'm good, sir.
Okay. So lastly, we'll look at a forecasting example and this idea of Bass forecasting model. You can see it published by a guy named Frank Bass, late 1960s, 1969 there. And it's trying to help with a harder problem, right? We won't talk about forecasting until the very last lecture of this class, and we only kind of briefly touch on it. But a lot of forecasting is built off the idea of having historical data. I've got a product. I've been selling it for, let's say, 2 or 3 years. I now have data about how it has performed as far as how many units were sold, potentially every week throughout the year. And now I have some history, right? And then I can say, okay, now that I have this history, I can build statistical models against that and say, okay, if it's going to perform similar to the way it's done in the past, at least in the short term, for instance, can I make accurate predictions in the short term? But notice that as I'm saying this, a lot of this depends on a past history of the model. And the batch forecasting is more off this idea of a new product. And so you're saying, okay, how do I do that? And so things that are parts of the model that are used to estimate with the nonlinear optimization problem are these MP and Q variables. In this case, the decision variables for us. And so M is the quantity of the people estimated to eventually adopt the new product. So again, that's something I'd probably want to know if I was a person in like a sales manager's position, as far as, okay, what is the total population of people that I think would ever purchase my product? Q and P are these coefficients. You can see they're imitation and innovation. So Q, coefficient of imitation, is the whole idea of this word of mouth. Hey, my friend has it. They're going to start talking about it. It's going to make me want to have it as well, type of scenario. Whereas the P, the coefficient of innovation, this is more of, hey, I learned about it, and without talking to anybody else, about just thinking of it between me and this marketing, whatever, this advertisement that I see, I want to go get this item because of my own interest there. So those are two different kind of mechanisms, if you will, that would influence somebody's desire to obtain a certain product. And so with this, we start talking about this whole idea of likelihood of adoption. And so you can see the formula here, and notice there's a sum. There's a sum of two different components. Well, the first one, P, is the coefficient of innovation. And notice it's by itself, right? And that kind of makes sense because we influence this as the individual's own interest, right? But then we have Q, which is this imitation, and the Q is multiplied by something. And what is this something? Well, C sub T minus 1 is this quantity of people who have adopted the product through time T minus 1. And notice it's divided by M. So if you look at that ratio here, basically you're talking about the fraction of people that will ever have adopted your product. This is an estimate there. And so it kind of makes sense that this has to do with the number of people that have the product, that are out talking about the product, and we're multiplying it by this coefficient of imitation there. All right. So with that being said, we say, okay, this is our adoption likelihood. Okay, that's good. Now to forecast with that, we look at something like this. And so I say, okay, this term on the left is the adoption likelihood. You can kind of see that gets mapped down here. And the term on the right is the remaining amount of people that have yet to adopt, right? M is the total minus the number of people that have adopted this far. And we'd say, okay, that's the forecast of time t. So basically we're at some time t minus 1. We're forecasting for the next time interval. We're using things like the two different coefficient, imitation and innovation, this M estimate. These are all three parameters, and then a little bit of historical data of what people have adopted in the first. And so this will be like something like, okay, if we have a similar type of product that got released and we're kind of modeling this one after the behavior of that one. So the model itself looks like this. Here we have an error term defined, which this little f is going to be the forecasted value and the s is going to be the actual value. So we have ft minus st, so that gives us an error term. And we're just minimizing the sum of squared errors. So again, that's exactly what we talked about before, right? We said we were going to minimize the sum of squared errors. I said that's a common thing with respect to forecasting, and so there it is in our objective function. Subject to what? Well, we've got some forecast terms here. And so for every time in the time step here, we're just implementing this formula. So if I look, this and this are the exact same. And we're saying it's got to be greater than or equal to 0. And P, Q, and R are elements of the real numbers here. Okay, so M I'm saying is greater than or equal to 0. And I do not say P and Q here are. M has to be greater than or equal to 0 there because of what? Well, M has to do with the number of people that are going to eventually adopt the product. I cannot have a negative number there, right? 0 would be nobody. I introduce a product and very bad day. Nobody was interested in it. Nobody ever buys it, right? So a total flop in terms of new product launches, if you will. Whereas P and Q, I guess, would be kind of these ratio, these probabilities. Could you have an adverse effect as far as when people talk about it, they all are bad mouthing it essentially, so driving it in the opposite direction essentially. And so the example we'll talk through tonight is this idea of a forecasting the independent studio film. So basically we're saying, okay, but we're going to use some data similar to another film and then be able to say, okay, this film behaved this way. If I think of another film that's similar to it, maybe it'll feel similarly and be able to work off of that data set. So another way of thinking about it is if I launch something and it's starting out and I'm starting to record the first few weeks of it and I want to explain this model off the data I do have and then be able to show the trajectory there. Another thing that we're seeing as far as we're seeing revenue and we're taking that as a analog to the number of people viewing the model here. And that's where the N is going to come into place there. As far as, okay, this the people that are actually going to view the model. Okay, revenue is kind of a loose correlation with that. So as far as, let's assume that there's a static charge as far as ticket price. And then the only other flaw that I could think of that in terms of the model would be, what if somebody comes back to see it more than one time, essentially? And so we'll kind of assume that those are causing minor errors in the model, but the model is still useful. We still have P and Q. Those are the same things as always. M is here. This idea of minimizing the sum of squared errors, we have 12 different time steps here. So it'll be the error of time step 1 all the way to the error of time step 2, all of them squared individually. Subject to, these more or less will follow the same idea that we've described here, except for usually the kicker is how do you start? The start point here, if I'm sitting at the very first part, how do I look back one from it? And so if you do that, you'll see that, okay, that C sub t is essentially 0 when I start that first one. So I got 0 here and 0 here. This term that's the forecast term basically just becomes P times M. And so that's what I'm making the note here that, okay, that very first forecast term will be P times M. And then after that, the remaining forecast terms for time steps 2, 3, all the way to 12 is just that forecast formula. The error term after every forecast is just the actual, FT minus ST, with the usual bounds down below. Just showing this in Excel, and we're actually going to look at 2 different variations of Excel here. All right, here's one. And so this is just the data that I give you. Decision variables here. This is the sum of squared errors, right? So the sum of that column, that should make sense. The error column also, it's pretty straightforward, right? We're making forecast of weekly revenue. So I take the forecasted value minus the revenue value, and I square it for every one of those. That's interesting. This is where really the magic happens, is in this column. Like I was saying before, you have this starting problem always with these forecasts here. And so how do you do the first one? Well, it's just P times M because I can't look backwards. There's nothing in the cell above it in this case. So that's good to note. And then finally down here, I have the usual formula. This formula that you're seeing right here is this right here. P plus Q times cumulative before divided by M is the first term. So it's C20 is P plus D20 is Q times cumulative before. I'm in time step 2, so I go to cumulative up here of time step 1 divided by M. Hopefully that makes sense as far as when I'm jumping up to the cumulative there. And then I just drill that all the way down as far as this goes down. Notice here I'm on time step 4 and I'm reaching back to cumulative 3 there, right? That's the T minus 1 business that I'm having to work through. So those subtle things are probably what's the best things to take note of here in this forecast formula. Other than that, this problem only has 1 or 2 other tricks in it, and I guess things to be aware of. Oops, I don't need to get the VBA editor. And so this is what I'm showing here. And the whole idea here is, yes, this is solved, and the way I've saved it is solved in the correct solution there. but you do have to be careful. This problem is not the same as all the ones we've talked about so far. One of the ways you can think of that is look at this term right here. Remember, P, Q, and M are the decision variables. Think of the nonlinearity parts of this. I have mixed terms, P times M, right? Think of the FOIL method, if you will. I have a division here, right? Q divided by M, and then I'm going to multiply that by M. So, okay, the M will cross off there. I'll give you that. But I'll have Q times M, right? So I'm going to have P times M there and Q times M there. So this is where we're going to have some things that are going to force this to not be a quote unquote nice function. And by nice function, I mean we do have to be careful here of shooting at a local optimum. And so that's where I have some notes here as far as this is the case where in here, I would probably start playing around here as far as use multi-start. With multi-start, you do have to bound your decision variables here, and that's why these are extra ones, right? B20, C20 here, I'm just kind of starting to pick these. Usually what I would suggest doing is picking these things being very wide and then kind of narrow them down. And then also the coefficients 1 and -1, think of those as kind of probabilities. So living between 0 and 1 tend to make sense there as well. So just be aware of that. You can get it to solve that way. The other way to do it is through the evolutionary solver. This guy here, model is exactly the same the way it's set up here. But now if I go to the data, okay, setting some bounds here as far as, okay, there's 100 there, 1 and 1 are the bounds here. I'm putting it at evolutionary. This is where you can start playing with down here as far as how much mutation you want. This is a tolerance, how much it's going to be changing until you get to a convergence, a termination of the application, population size, so on and so forth. Just to show you this run, essentially, when I hit solve, you'll want to look down here in the bottom left here. And so just to talk through this a little bit, notice it's just kind of like shaking, quivering there a little bit there. And so it's going through different sub problems and different trials here, right? And so basically what these trials or the sub problems are the generations. Think of it that way. And this idea of the incumbent is this is the fittest candidate or one that's found so far. And it's saying, okay, I can't improve on the current solution. I think that was because I had these already in place here. So let's delete these off real quick and run it again. So we set it up here. Now notice here it's starting to move around here, right? 4.6, 4.5, 4 point. Think of this as the best candidate solution that's found up to this point in time there. And so it's going to try to drive itself down. I think it's 4.49 or something like that was the last one. Yeah, 4.49 there. And so you can kind of track the progress of that as far as saying, okay, this is how it's driving the minimization of that sum of squared errors lower and lower there essentially at that point. At this point, it's going to find a terminal condition there to terminate that execution. In this case, it has, can't improve the solutions, and it's giving you the result there. In this case, I don't know if I think I graphed it on this one. What you'll end up seeing is something that looks about like this, or that historical one is in blue, but then that forecast one does kind of capture that hump and the decay that's happening afterwards as well there. And that's really the takeaway we're taking. We're trying to estimate the M, P, and Q parameters of the vast forecasting model to try to fit that historical data as best as possible. So hopefully that makes sense to you as far as what's happening there in terms of the model, the construction of the model, but then also just gives you a little bit of a thought there as far as how that's going to impact the solver parts there. And this is one where you have to play around with it a little bit differently. I definitely suggest you explore the whole idea of multi-start, the whole idea of the evolutionary algorithm there as well. In the Python space, I do something similar to that here. Notice there's a little bit more code here. I basically built out the idea of defining the model and solving the model as two different functions. So what I'm doing through here is kind of like a search type issue here, the multi-start in Excel. As far as I've got three variables here, population that's going to adopt the innovation coefficient and imitation coefficient, and I'm basically walking over a nested set of for loops here to kind of do a grid search over those three different dimensions. And then I'm passing at every point on those grid search values in to develop a model. Now that I have the model, what's different about the model? You say, okay, it's the same model except for I'm setting some initial values, which is something you can do in Pyomo. Right, where are we at here? Right here. This is where they get set. And so basically, this is allowing me to kind of think of that multi-start idea as far as setting it at a different spot in the search space and then letting it go from there. And then, okay, I say, okay, let it go from there, let it find what it thinks as an optimum value. And then what I'm doing is I added logic really down in here that says, okay, if the search result is optimal, go down here. And basically this section of code here is just keeping track of, okay, have I hit the best solution here? And so that's what this is. At this point, then I'm basically keeping track of that best model, and I get very similar outputs here that I was doing in Excel there. So I'm basically having to hand code a little bit in the Python space, that whole idea of multi-start and the whole idea of searching at different spots on this search area and then keeping track of the best one there. So it's not terribly difficult. It's not terribly complex as far as the logic, but definitely you as the analyst are taking control or taking ownership of that logic and having to write it out yourself with the way I'm doing it there. All right. I think that gets us to everything that we wanted to talk about in terms of the fast forecast model, just the same type of fit there happening with the Python code, just showing that that is producing a similar result in Excel. All right, so that gets us to the end of chapter 8, the end of nonlinear optimization as we're talking about it this evening. Hopefully you're appreciating that a little bit as far as what that solution looks like and how that all is working together. Hopefully I've talked to the point that you appreciate the complexity there. There's a layer of complexity with nonlinear that is not there with the linear programming there, and so what makes it more difficult, even though the difficulty is a lot of times, again, hidden away from you from this class's standpoint, as far as just interacting with the solvers differently. So I guess, Rakesh, do you have any questions on your side?
Uh,
All right.
I'm
So,
fine, sir. So far, so.
okay, good. So I guess at this point, just pointing you at the homework as far as for the week, usual situation here, 2 attempts, takes the highest. It's open now, should be closing on the 23rd, which is next week there. I haven't posted the module for next week, but I'm pretty sure we kind of enter a different phase of the lecture at this point. At this point, we've basically been pursuing this thought of optimization and linear programming, now nonlinear there. The next few lectures are going to be more topical in nature, as far as we talk a little bit about inventory, talk a little bit about queuing theory and those type of things there. So it does feel a little bit different there as we kind of branch and kind of touch on other areas in the overall domain of operations research there. So that's kind of where we're sitting at in terms of the semester.
Yes.
All right. So I guess if you don't have any immediate questions, I think I'm done for the evening there.
Next week, are you taking physical or remote class, sir?
Most likely, I think I'll be back on PSU campus next week.
Okay.
I was traveling a little bit this week. That's why I had to do it remote there. But yeah, I'll try to make it back to PSU next week.
Oh,
But
yes, sure.
I guess on Sunday, Sunday or Monday, I'll send out my announcement and be able to tell you for sure at that point.
Yes.
All right. So I guess if there's no other questions, I'll go ahead and shut down the meeting and have a
See you, sir. Have a good weekend.
yes, you too. See you later.
Yeah, see.